Hi guys, today we're going to be talking about average rate of change. So to get an idea about this concept, let's talk about something that we all know about. We're all familiar with the concept of speed. If you drive a distance of 120 miles in 2 hours, then your average speed or rate of travel is 120 miles divided by 2 hours, which gives you an average speed of 60 miles per hour. Now, suppose you take a car trip and record the distance that you travel every few minutes. The distance you've traveled is the function of the time t. So we could think of this as s of t, that's our function, is the total distance traveled at time t. We can graph our function, this is a graph of this function. It shows that you have traveled a total of 50 miles after 1 hour, 75 miles after 2 hours, 140 miles after 3 hours, and so on. So we have this nice curve here, right, modeling out the amount that we have driven over a period of time. To find your average speed between 2 points, any 2 points on this trip, we divide the distance traveled by the time elapsed. So let's go ahead and calculate your average speed between 1 and 4 p.m. The time elapsed is 3 hours total, right? Because if we're at 4 o'clock and we started at 1, that means 3 hours have passed. Now we want to find the total distance traveled. So between 1 o'clock and 4 o'clock, we can see that we have gone here we're at 50 miles, and by 4 o'clock we've traveled 200 miles, so we've gone a distance of 150 miles total. Thus, our average speed now we can calculate. The average speed is the distance traveled by time divided by time elapsed. So 150 miles divided by 3 hours gives us this rate of 50 miles per hour. That's our average speed we traveled. The average speed we have calculated can be expressed using function notation. So this might look slightly familiar to you because it's really related to our slope formula, if we recall, which was m equals y2 minus y1 over x2 minus x1. And here we can see that we have two x values for our time, and then here instead of saying y, we're saying the function value at that time. Then we're putting in here our known values, right? 200 miles minus 50 miles over 3 hours to get that average rate of 50 miles per hour. Note that the average speed is different over time intervals. So if we were to look at that again, we can compute a different average rate of change for a different interval, and we'll find out it's a different answer. So here now, if we look between 2 o'clock and 3 o'clock, if we want to find the average rate of change or the average speed of that time, it's going to be the function value at 3 minus the function value of 2 over 3 minus 2, right? Because those are our x values. And here it turns out we get between this time, the average rate of change is 65 miles an hour when we compute this quotient. Finding average rates of change is important in many contexts. For instance, we may be interested in knowing how quickly the air temperature is dropping as a storm approaches, or how fast revenue is increasing from the sale of a new product. So we need to know how to determine the average rate of change of the functions that model these quantities. In fact, the concept of average rate of change can be defined for any function. So any equation we look at can use this concept of average rate of change. So we should definitely recognize this, right? The average rate of change of the function y equals f of x between x equals a and x equals b equals the change in y over the change in x. And if you recall, when we've looked at the slope formula in the past, we have written it as delta y over delta x, which is the change in y over the change in x. This right here, though, is our new notation, right? That the average rate of change is the function value of b minus the function value of a divided by b minus a. And remember that this is just two x values is a and b. And then these are the, when we plug those x values in, the function output that we get from them. The average rate of change is the slope of what we call a secant line between x equals a and x equals b of this graph of the function f. We call it a secant line. This word secant comes from the Latin word secare, which means to cut. So if we notice, this is a cutting line, right? It doesn't always go through the entire curve. It just connects 2 points, right? It's the line that passes through A and f of A and B with f of B, right? Where B is, we compute f of B by plugging in B to an equation, right? And here again we have this formula, f of B minus f of A over B minus A for our average rate of change. And again, it's just telling us the slope of this dotted secant line that cuts right through the graph. Okay, so here for this function, f of x equals x minus 3 squared. The graph here is shown, and we want to find the average rate of change between the following points, x equals 1 and x equals 3. And then for b, we're going to look at x equals 4 and x equals 7. So if we want to compute the average rate of change between the points 1 and 3, then we need to calculate the function value of 3 minus the function value of 1 over 3 minus 1. So now we have to be a little careful. We were given this equation, right? X minus 3 squared. So here, x is 3, so 3 minus 3 squared, well, that just becomes 0. And then we're subtracting from that 1 minus 3 squared. Well, that's going to give us negative 2, right? 1 minus 3 is negative 2. But then recall that when we square negative 2, we're going to get positive 4. Anytime you square a number, you'll always get a positive value. We're still subtracting that, though, so let's be careful with the sign errors. So we end up getting 0 minus 4 on the top. And then 3 minus 2 is going to result in 2 down here. So we have this is equal to negative 4 over 2, which indeed results in a slope of negative 2. So in this part of the function here, between 1 and 3, the slope of this secant line is negative 2. For every, it will move down 2 and over 1. And we can kind of see that here between 1 and 2, that we're starting here at, let's see, 1, 2, 3, 4. We go down 2 and over 1. And yes, it looks like if we go down 2 and over 1, we are right on our curve. Now let's go ahead and look at computing between 4 and 7, right? That's our second interval, was we wanted to know what is the average rate of change here between x equals 4 and x equals 7, that interval. Again, here's our function notation, f of 7 minus f of 4 over 7 minus 4. Filling in this equation, f of b minus f of a over b minus a, right? That's what this is. And then computing the actual values using the equation given, right? So 7 minus 3 squared minus 4 minus 3 squared over 7 minus 4, right? Just plugging in values here. And then we'll end up with 16 minus 1 over 3, which gives us 15 over 3, which indeed is 5. So here this line rises 5 for every 1 it moves over. So between 4 and 5, it's going to go up 5 units and over 1. Okay, this one is a little bit different because here we're looking at, this is kind of giving us an introduction into our next subject. We're looking here at the average speed of a falling object. If an object is dropped from a tall building, then the distance it's fallen after t seconds is given by the function d of t equals 16t squared. If we recall, 16 is the coefficient for gravity, right? And it's only because we have this t squared that it becomes 16, but that is actually taking effect, that's the effect of gravity on a falling object. To find its average speed, or average rate of change over the following intervals, we're going to calculate between 1 second and 5 seconds. But then B here is the one that's going to get a little bit different. We're going to compute, rather than a numeric value, we're going to compute a variable value, and then a double variable value, right? A plus h is our second t value. And this is actually a pretty special setup that we've got going here. So we're going to look at that much more deeply. Okay, for the first part of our equation, we know that we're using this 16t squared. So if I want to know between 1 and 5 seconds how far an object falls in free fall, and this is basically an object that's just dropped, right? It's not thrown with any velocity. It's just dropped off of something. So if we calculate the distance at 5 and the distance at 1, when we're using 16t squared, we do need to be a little careful here, right? This is 16 times 5 squared, so 16 times 25, minus 16 times 1, so we get 400 minus 16, over 5 minus 1. For an average, this is how far we've fallen, right? That's the speed of this falling object is 96 feet per second. So this number is an acceleration speed, or an acceleration unit, whereas here this is telling us about speed, and speed and acceleration are two different ideas. Okay, so here we are. We're going to take a look at this, how we calculate for the values of a plus h and a. So this is going to give us a little bit more difficulty because of this right here, a plus h squared. I'm going to go ahead and write that up here for us so we can think about what a plus h squared is, how they got this piece right here. Well, we know that a plus h squared is the equivalent of a plus h times a plus h, right? That's equivalent here. And when we have two parentheses like this, where we've got a plus sign in there, this is telling me I need to FOIL. If we recall foiling, I need to multiply the first pair, the outside pair, the inside pair, and the last pair. So first, a times a is a squared. Outside, a times h is plus ah. Inside is a times h. We get another ah. Now I'm going to do the last two pairs, right? Which would be h times h. So h squared. So I have, from that foiling, I got a squared plus ah plus h squared. That can be simplified a little bit, right? We can combine the ah's, so a squared plus 2ah plus h squared. This is what we've got from calculating a plus h squared. Now, because we have two 16s, a 16 and a 16, they're able to pull those out in front and just basically factor that 16 out. So we can simplify what we've gotten from a plus h and then a squared. So this first section, right, a squared plus 2ah plus h squared, that came from this foiling we did. Then we're subtracting from that this a squared. So these two pieces here are going to cancel out. Let me go to my next page. So here you can see that they've canceled, right? We have canceled out, so let me see if I can show you here, right? These two a's, we have a positive a squared and a minus a squared. So they cancel, so we're just left with this inside. And that's 16 that was out in front. So we have 16 times 2ah plus h squared over h. Now, we've got a common h inside of here. That's what happens here, is they factored out the h from inside this parentheses. So we're left with 16h times 2a plus h over h. Now, the reason for this is we would like to factor out and cancel out this h if it is at all possible. So pulling this h out of the top here has now allowed us where we can do a cancellation of those two h's and be left with this simplified expression. And then if we knew what this height differential is, we would be able to calculate, if we had these two values, we could calculate this speed of this falling object. But a lot of times in our course we are going to be looking at things that are more variable in nature, and this is actually a special example. So let's talk about that a little bit. We're going to talk about this more tomorrow, but that average rate of change that we just calculated is known as a difference quotient. And in calculus, we use difference quotients to calculate instantaneous rates of change. Everything we've looked at up till now has required us to use this concept of a secant line, right, that cuts through our function and gives us this average rate of change here. Well, it turns out when we get to a calculus course, we are capable of using just one point on it and finding what is called a tangent line and the instantaneous slope of that line. So that is where we will end for today. I do have some homework I would like us to take a look at before we totally leave for the day. I have put this worksheet online that is asking us to calculate some average rates of change. Please notice that I have crossed out 1 through 8. We don't need to really worry about going back and working on calculating slope, but I would like to work on 9 and 10 with you, and then we'll look at, actually, how about this? We'll do number 9, and then we're going to do number 21 together. So let me zoom in a little bit. Number 9 is asking us to calculate from this given table. So it's asking us to calculate the value over this interval from 1 to 9. And we have this table to get our function values from. Sorry, I'm folding a piece of paper so I have somewhere to work for us. So we know that our first x value is 1, and our second is 9. And so we want to find what is f of 1 and f of 9 from our table. Well, it tells me here that for 1, the function value is 3, and for 9, it's 15.8. So to find our average rate of change, we need to calculate f of 9 minus f of 1, recalling that if we remember, we typically are going to start with the value that is further to the right of it, but we could do 1 and 9 reversed. We'll just get a double negative answer that is a little bit more easy to make an error on. So it's always easier usually to calculate the larger value first, and then that's divided by 9 minus 1. Well, we know from our table that f of 9 is 15.8, and f of 1 is 3, and then we still have 9 minus 1 on the bottom of our problem here. 15.8 minus 3 gives me 12.8. And then that is divided by 8. And when I put that in my calculator, I get 1.6 as the average rate of change. So for number 9, my solution is 1.6. And for this homework assignment, due to there being so kind of little room on the page, I am going to ask you to please use a second piece of paper to write your solutions on. Now let's go ahead and look at problem 21. We're given this equation, or this function, f of x equals x squared minus 4x minus 12 on the interval from, that's this closed interval from 0 to 1. If you notice, it's always closed because we're always including these endpoints. So let's go ahead and see if we can calculate some of this information. Let me zoom out just a little bit. Okay, so we started with our function, and we need to find what is f of 6 and what is f of 0. Well, our equation that we were given for the function is that f of x equals x squared minus 4x minus 12. So let's go ahead and plug 6 in for x. We have 6 squared minus 4 times 6 minus 12. Then we know 6 squared is 36. 4 times 6 is 24. And subtract from that 12. Well, 24 minus 12, let's actually, excuse me, sorry, that was not the way I should be going about this. 36 minus 24. Got my calculator here. 36 minus 24 minus 12, that gives me 0. So the function value at 6 is 0. Let's calculate the function value of 0. We have 0 squared minus 4 times 0 minus 12. Well, these first two terms are just 0, right? Because 0 times anything is 0. So here we're going to get negative 12. So we've now got our two values. F of 6 is equal to 0, and f of 0 equals negative 12. Now let's go ahead and plug this information into our formula. So f of 6 minus f of 0 divided by 6 minus 0. We have 0 minus negative 12. Ooh, look at that. Easy chance for a sign error. Over 6 minus 0. We have a negative negative. So this becomes positive, right? A minus minus is positive. So we've got a positive 12 on the top over 6 for a final answer of 2. The instantaneous range of that function on the interval from 0 to 6 is positive 2. Hopefully you guys are doing well in the course. If you are struggling and have any questions, please email me. I'm also available for video chat. So please just let me know if you're struggling with anything. Today's the last day of our course for this week, so you have the 3 homework assignments that we've had. Please make sure you're filling in the attendance assignments. All you do is just return them to me, but it's my way of tracking that you're actually checking in with our class. So have a great weekend, you guys, and I will see you next week.